Welcome back, physics fans. Here we go with number 7 on the work power energy worksheet for grade 12 physics. From rest, a 400 Newton force pulls a 20 kilogram block up a slope that has a coefficient of friction of 0.55 at an incline of 30 degrees for a distance of 25 meters. So we have an inclined plane, an object on an inclined plane. It's only 30 degrees. There's a coefficient of friction of 0.55, and he's starting from rest at the bottom and pulling it up 25 meters using a 400 Newton force. So we have a lot of questions here. But before we start doing any of the questions, we're going to be doing them with work. You can see work, 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 work. So we'll need forces because work is force times distance. So we'll go to that part of the chapter that we finished a while ago and draw our free body diagram. There's our object. We have a normal force. We have a force of friction slowing it down from trying to go up high, and a gravitational force. And most importantly, our push force, 400 newtons up. Okay? And remember, stop me if there's any questions. Please, even if it's an online one, here we can pause it and take a look at it. So, we remember when we did this chapter, we instantly, before we started solving things, we just plugged into the assigned force of gravity in the x direction. That's the direction of motion, or as some people called it, F parallel. Fgx was mg sine theta. Okay, and I'm just going to do that right here. The mass of this object is 20 kilograms, so 20 times g, 9.8, times the sine of 30, and that is 98 newtons. So the force of gravity pulling this 20 kilogram object down the incline, that's the force of gravity in the x direction, and I'm not drawing it in my free body diagram because that would be wrong. Okay, once again, drawing this component would be wrong, and drawing that component there of the gravity would be wrong. You're not drawing components of a in a free body diagram. What is the force of friction? The force of friction was mu mg cosine theta, which is mu times n, and n is mg cosine theta. So mu is 0.55 times m, 20, times g, 9.8, times the cosine of 30. And we'll have a frictional force that's stopping our pull force, which is 400, of 93.357 newtons. 358 actually, if you want to do the rounding up of that fifth sig fig. And the net force. Okay, the net force is the pull minus the force of friction minus the force of gravity in the x. Because the force of friction is down because we're moving up. The force of gravity is also down because gravity is always down, and the pull is up. So we'll take the 400 minus the force of friction, which we just calculated, 93, minus the 98, and we get a net force. The net force pulling the object up the slope is 208.64. Okay, we needed these forces to do the work of work. A, calculate the work done by the pull force of 400 newtons. So the pull force, I'll just even write down pull force in here. You don't need to. It's going to be work is equal to F pull times the distance it moves. They'll be in the same direction. The pull force, or the pull, I said push here, should probably be pull, don't matter, is 400 newtons. So it's 400 newtons times the distance it moves up, which is 25 meters, and that product is 10,000 joules. B, calculate the work done by friction. Work, let's do the friction one here. So the work done by the frictional force is equal to the frictional force times the distance. The frictional force is going to actually be negative 93.58. Well, realistically, 358, sorry. Realistically, we don't put negative into the formula, right? Because work is equal to the force times the distance times the cosine of the angle. But this will be the cosine of 180 degrees because they're in the opposite direction, and that's negative 1. Times the distance of 25. When we do that product out, we get negative 2,334 joules. So that's how much energy will be taken away from our push force by friction, and that'll go to heat. Might even go to a little bit of sound and stuff like that, but we'll just say that it all goes to heat energy. C, the normal force. The work done by the normal force is going to be the normal force times the distance, and again, I'm just going to write it down here, cosine of the angle. And so the normal force, I haven't told it to you, but it's 169.7 newtons. And we have to multiply that by 25 meters, but we're also going to multiply it by the cosine of 90. That means they're perpendicular to each other, and that's just 0 joules. OJ. Because it's not moving in the direction that the normal force is. Okay, gravity. The work done by gravity, D. So the work done by the force of gravity is the force of gravity times the distance times the cosine of the angle. Okay, and when we put in 100 and now that's the cosine of the angle between the distance moved up. So that is the direction. Sorry, I should probably do this in the box here. The D is this direction up the slope, and force of gravity is this way. So we need to have that angle. And that angle is 150 degrees. I think. Or is it 120? It's 120. Okay. And this is going to equal 196, that's its weight, times 25 times the cosine of 120. And I'm just going to pull up the calculator and do that just to verify that I'm doing everything right. 25 times the cosine of 120. And I get negative 2450. Now, some people might have done this differently, the gravity one. They might feel more comfortable doing it this way because we've learned to do it this way. Observe, when you move an object from here to here, what is the work done by gravity? You just want that height. And if this is 25, and that's 30 degrees, to get that height, you'd get the sine of 30 times 25, and this is 12.5. And then you do 12.5 times 196, and you get 2,450. So you could have done it by the change in potential energy. Those people that feel comfortable doing it that way, just understanding it. Okay, just leaving it alone. So the work done by the net force is the next one. Now the work done by the net force up the slope, since we have the net force is 208, work done by the net is going to be F net times D. Okay, they are in the same direction, so I won't even put the cosine there. This is 208.64 newtons times the D, which is 25, which is equal to 5216 joules. Now, F is calculating the net work again, but using the answers for A, B, C, and D. Why do I add up A, B, C, and D? Because these are all the forces. Looking at the free body diagram, these are all the forces. So the work done by all these forces would be the net work done. Add up the work of all of them, and you get the net work done. So let's do it another way. The sum of the forces work. So the work done by the sum of the forces is equal to 10,000. That's A. And we add B, which is a negative 2334. We add C, which is 0, so I'm not even going to do that. And then we add D, which is 2450. And that also equals 5,216 joules. Okay, light bulb moment, right? We can get the net force times the distance to get the net work done, or we could just add up the work done by all the forces and get the net work done. So, let's see, I think I've changed this since then. The energy put into the system is A. The energy that went out of the system is D and B. Where did the rest of the energy go? In other words, we have calculated this net work done, 5,216 joules. Where did it go? Is it just sitting on the ground? See, we put in 10,000. Understand, our push force, we applied this much and put 10,000 joules into the system. What happened? Well, it went up against gravity. So some of it went into gravity, potential energy, and some of it went into the heat that was produced. Yeah, that's good. That's good. But we're an accountant now. Where did the rest go? That's good. But you're still missing 5,216 joules. Where did that rest go? Yes. Where did it go? Where did it go? Answer me. Hmm? Is it still in the system? Yeah. It's still in the system. It had to be in the system because we added 10,000 to it. It went into friction, gravity, and motion. It started from rest and it's speeding up. It's speeding up. We have a net force. You understand? We have a net force that's not zero. That means the object is accelerating. So the rest of this energy went into kinetic energy. The kinetic energy is 5,216 joules. The rest of it went into kinetic energy, which is going to be our 1/2 mv squared. This gives us v is equal to the square root of 2 times 5216 divided by its mass, which is 20. This square root is 22.839 meters per second. Okay? So we were able to calculate through the work done by the pull force, the work done by the friction force, the work done by the gravitational force to get the net work done. The net work done. Got it? And therefore, we put that into kinetic energy, what's left over, and we were able to then to calculate the velocity. Now you go, yeah, so what? Okay, we calculated the velocity without using Newton's second law. We didn't ever calculate the acceleration or the time. That's pretty special. This was a totally different way of doing it, calculating it using energy. We were able to get a speed without ever having to use acceleration or any kinematics. No kinematics here. Okay? But now that we've done it, how would we do it with kinematics? And sorry, I did H right in here in G, so I didn't need H. Kinematics. So F net is equal to, what was it, 208.64 newtons, and that has to equal MA, and M is 20. So now let's do kinematics. Acceleration is 208.64 divided by 20. I'll take this and divide it by 20. We're doing the kinematics way. It's accelerating. It's accelerating up the slope stinkingly fast at 10.4321 meters per second squared. The initial speed is 0. The distance is 25 meters. So calculate the final speed. Vf squared equals Vi squared plus 2AD. I'm already showing the square root there. I'm already jumping the gun, sorry. And this equals Vi, 0 squared, plus 2 times 10.4321d, which is 25, all square rooted. So we'll take this number, do the square root of 2 times the number we have there, acceleration, times by 25. And we get the same number. It's nice. Kinematics way works as well. Hope so. We've been using it all along. Big smiley face there. There we go. Oh, yeah. Okay, hopefully this is a big light bulb moment for you, that we could solve it with energy, or we could solve it with kinematics and Newton's second law. Oh, it's beautiful. This gives us a little bit more interesting information. It gives us the heat, right? It gives us the heat. Anyways, thank you very much. Subscribe, like, comment below. And if you have a bad comment, leave it on someone else's channel. Thank you. Bye-bye.